Assalamu alaikum. So let's continue with the state space representation uh, in discrete time system. So simply given nth order difference equation, we need to rewrite it such that it's written as n first order difference equation. So let's start with a simple example here. Find the state variable model of the following discrete equation: y of k plus 2 equal to u of k plus 1.7 y of k plus 1 minus 0.72 y of k. So this actually is a second order a difference equation. Now we need to rewrite it in terms of two first order a difference equation. Now see, someone will say, if I'm having y of k plus 2, how many delays I need in order to generate y of k? So the first one I need, the first one, y of k. So the first delay that I need in order to generate y of k plus 1. Then I need another unit delay, z minus 1, in order to generate y of k. Now the idea is very simple. The output of each delay is a state variable. So here the output of the first delay is x. I will call it x1 of k. And the output of the second delay, which is the y k plus 1, is the second state variable, so it will be x2 of k. So simply here we can write a note: the output of each unit delay is a state variable. So simply this is a second order. I need two states to represent it. So here x will be element of R2 by 1 because I need two state variable in order to represent a second order system. So if n, in case of nth order, we need x to be element of Rn by 1. So now let's try to write this equation in terms of x1 and x2. So x1 of k actually is y of k, and x2 of k, according, it will be y of k plus 1. So simply this means that the value here will be what? The value here will be x of 2 k plus 1. The same thing here. The value here in terms of the x1 will be what? Will be x1 of k plus 1. So simply, now we have the state variable. We will say that x1 of k plus 1 will equal to x2 of k. Yeah. And now x2 of k plus 1 will equal to y2 of k, which is u of k plus 1.7 y of k plus 1. Y of k plus 1 is x2 of k minus 0.72 y of k is x1 of k. So this is the state model. But the state space representation or the state variable model also should include the output. The output is something that we are interested in. Now from here, from the definition, y is equal to x1 of k. So here we can write y of k is equal x1 of k. Now we can write it in matrix form. We can say x of k plus 1, which is a vector now, consists of x1 k plus 1, x2 k plus 1 will equal to a 2 by 2 matrix multiplied by the x1 of k, x2 of k plus a 2 by 1 matrix, because we have only one input here, multiplied by u of k. So the first equation should read as x1 k plus 1 must equal x2 of k. So simply this means that this will be the 0, this will be the 1. You cannot see any input here, so this will be 0. The second equation, x2k plus 1, which is this one, the first thing I will collect the term of x1, which will be minus 0.72. Then I will collect the coefficient of x2 of k, which is the 1.7. Then I will collect the coefficient of the input, if we have, and here we have 1. And for the output, y of k written in terms of the state x1, x2. Let's omit it kk here, and it will read as x1, so this will be 1 0, and there's no input here. So simply the general form for the state variable model can be written as x of k plus 1 is equal to a certain matrix, a state matrix we will call it later, x of k plus b, which is the input matrix, u of k, and y of k, the output equation, will equal c x of k plus d u of k. Now, where x is element of Rn, where n is the number of state variables, which is mean that the order of the system. N by 1, of course. And if x is order n by 1, then A will be a square matrix element of Rn by n, and this is called the state matrix. We call it the state matrix. U element of Rm, where m is the number of inputs. So simply this means that B will be element of Rn by m. Now C, if we need to find a dimension, let's assume that Y is element of R of Q, where Q is the number of the output, so simply C will be element of RQ by N. This is element of RQ by 1. This is element of Rn by 1. So simply this must be Q by N. And we call this one the output matrix. Now D will be element of RQ by M, and it's called the direct input matrix. Why we call it direct input? Because we are directly connecting the input to the output. So now, what about if we have a transfer function and we need to write the state variable model? Of course, you should understand that the state variable model is ununique, and for that I will start with the following example. Find the state variable model The meaning is to find the A, the B, the C, the D of the following transfer function or the pulse transfer function. So let's assume G of Z will equal to Y of Z over U of Z, which equal to Z square plus 2Z plus 1 over Z cube plus 2 Z square plus Z plus 1 over 2. Now first here n is equal to 3. The order of the denominator here is 3, so this means that I need to represent this system using a 3 by 3 or first the order of the system is equal to 3. The highest power of Z in the denominator is a 3, so simply this means that I need a 3 state variable. So how to select the state variable? Now the first method that I will discuss with you is called the direct programming or the direct method. Or simply we call it direct method. And it will state like this. First thing, write y in terms of the transfer function, z squared plus 2z plus 1 over z cube plus 2z squared plus z plus 1 over 2 u of z. Now take the u with the denominator as a state variable, as x, vector x, let's say. So simply this means that this will equal n of z over d of z multiplied by u of z. So in the direct programming, I'm saying that x of z is equal u of z over d of z. Then let's write it here. So this will equal to u of z over z to the power 3 plus 2z squared plus z plus 1 over 2. Now this will equal to x of z multiplied by z to the power 3 plus 2z squared plus z plus 1 over 2, which will equal u of z. Now using the shifting theorem, this will equal x of k plus 3 plus 2x of k plus 2 plus x of k plus 1 plus 0.5 x of k will equal to u of k. Now put the highest sequence in one side, which is the x of k plus 3 will equal to minus 2x of k plus 2 minus x of k plus 1 minus 0.5 x of k plus u of k. Now, how many delays I need in order to find x of k? If I'm starting from x of k plus 3, so this is the x of k plus 3, using the first time delay, we will construct the x of k plus 2, another time delay, we are getting the x of k plus 1. Finally, we need another time delay in order to construct or find x of k. So remember, the output of each time delay is a state variable. So here we have the x1 of k. Here it will be the x2 of k. Here it will be the x3 of k. So we need 3 state variables because the order of the system was 3. So simply here x2 of k is equal actually x1 of k plus 1, and this one will equal to x2 of k plus 1, and this will be the x3 of k plus 1. So now we are on a stage to write the state variable model. So we start from x1 of k plus 1 will equal to x2 of k, x2 of k plus 1, x2 of k plus 1 is equal to x3, and finally x3 of k plus 1 will equal to the first one here is minus 2 xk plus 2 is equal to x3 minus x of k plus 1 is equal to x of 2 minus 0.5 x of k is equal to x1 of k plus the input, which is the u of k. So this is the state equation. Now what about the output? If we recall, here, we said that x is equal u over d. So simply this means that y will equal n of the multiplied by x of z. So now y will equal to the n, which was z square plus 2z plus 1 multiplied by the x. Now using the shifting theorem, I will find the sequence y of k will equal to, now this is z to the power 2, so the x of k plus 2 plus 2x of k plus 1, here I'm having z, plus x of k. Now remember, this actually is the x1 of k, this will be the x2 of k, and this will be the x3 of k. Let's put it here, see it? The x is the x1, xk plus 1 is the x2, and the xk plus 2 is the x3. So simply now we can write the state space representation in compact form. X of k plus 1 will equal to certain matrix multiplied by x of k plus the input matrix multiplied by u of k, and y of k will equal the input matrix, which is the c, multiplied by the x of k plus the direct input matrix, if we have, multiplied by the input. So let's try to fill the matrix. So the first equation is x1 of k plus 1 will equal to x of 2, so this will be 0, 1, 0. The second equation, x2 of k plus 1 is equal to x3, so this will be the 0, and the 1. There is no input in the first equation, here or here, so this would be 0 and 0. The last equation, the first coefficient here will be the coefficient of x1, which will be minus 0.5. The second coefficient will be the x2 will be the minus 1. The third coefficient here will be the coefficient of x3, which is the minus 2, and here we have input, so this is the 1. For the output, the first coefficient here will be the x, which is the 1, the x1, then x2, which is the 2, then the x3, which is the 1. And there's no input here, so this will be the 0. There's no direct input in the output. You cannot find a direct input. Actually, in physics, you cannot find a direct input, which means that you cannot find the input directly appear to the output. This means that I'm having a link between the input and the output without any dynamics. Now, this is very interesting, by the way, representation, very useful representation, because if I recall the transfer function we started with, which is the y over the u, was equal to z square plus 2z plus 1 over z cube plus 2z square plus z plus 1 over 2. So if we examine the shape that we have in the direct programming with the transfer function, we can get a very useful relation, such that if I need to represent the system or to find the state space representation in direct programming, I will get the phase conical form, or what we call the controllable conical form, which will start with x1 of k plus 1 will equal x2 of k, x2 of k plus 1 will equal x3 of k. If I'm having more, let's assume I'm having more, x3 of k plus 1, I'm having x4 of k, x4 of k plus 1 is equal to x5 of k. Let's assume it's 5 order. So finally x5 of k plus 1 will be a function of x1, x2, x3, and x4 of k. How it's written? Now see. So here starting 0, 1, 0, 0, 0, 1, which is a third order. So the third equation, this one, so the third equation now, this one, will be the coefficient of the third line. If I compare it with the denominator here, the first one is the coefficient of z to the power 0 in the negative sign. The second one here is the coefficient of z in the negative sign. And the last one here is the coefficient of z to the power 2 negative in the sign. And all the time, the B matrix will be zeros until the last equation, which will equal the 1. So what about the output equation? Y? The same thing. If you notice here, this one is the coefficient of the z to the power 0. This one is the coefficient of the z to the power 1. And this one is the coefficient of the z to the power 2. So simply this means that if I need to write the state space representation in what we call it the phase conical form or the controllable conical form, actually I don't need to go to the sequence. From my understanding, that the last line contains the characteristic equation in the negative sign, where the output equation will contain the coefficient of the numerator, and this representation actually is called the phase conical form or the controllable conical form. So I will give example to highlight that. Let's assume that we have y over u is equal to z square plus 0.6 z plus 7 over z square plus 1.1 z plus 0.2, for example. And I need to write the state space representation in direct, using the direct method or the phase conical form. So the first thing that I need two state variable, because here the order is 2. So this means that x of k plus 1, which will equal to x1 of k, x2 of k. Now the first, the input matrix, x1, sorry, this is +1 here, huh? Let's fix it. Sorry for that. So this is the x1 of k plus 1, and this is the x2 of k plus 1. So x1 of k plus 1 will equal to x2, so this will be the 0, the 2. Now the x2 k plus 1, so I will go to the denominator. The first thing here, I will collect the coefficient to the z to the power 0, and I invert the sign, so minus 0.2. Then I will collect the coefficient of the z, and I will reverse the sign, so this will be 1 minus 1.1. And finally, the b is already fixed to be 0, 0, and I'm having 1 only in the last equation. So here I'm having two elements only, 0 and 1, u of k. Now for y of k will equal to x of k. I don't have a direct input, so I will not write it. So I will go to the n. Then I will collect the coefficient to the z to the power 0, which is the 7. Then I will collect the coefficient to the z, which is the 0.6, and that's it. I'm finishing the state space representation using the direct programming. Now let's discuss another method, which is the parallel programming. Another way to represent the state space representation using the parallel programming. And I will start with a simple example. Let's assume that we have y over u will equal to 1 over z square minus 1.7 z plus 0.72, and I need to find the state space representation. So let's do it here for parallel programming, and here let's do it again for the direct programming. So here in the parallel programming, we will use the partial fraction expansion. So here using a partial fraction expansion, we can write y over u to be a certain constant, let's say k1 over z minus 0.9 minus k2 over z minus 0.8. So simply the first thing here, I factorize this one into its factor, so this will be the z minus 0.9 and this z minus 0.8, so distinct roots, so I can factorize it, where k1 will equal, now I will multiply this one by the root, so it will cancel, so it will be 1 over z minus 0.8 evaluated at z equals to 0.9, and this will equal to 10. The same thing here, we can find k2, which will equal to 1 over z minus 0.9 evaluated at z equal to 0.8, and this will equal to minus 10. So now the partial fraction expansion y over u will give me 10 over z minus 0.9 minus 10 over z minus 0.8. So after that, the method will follow the same. Y will equal 10 over z minus so now we can write y equal 10 over z minus 0.9 multiplied by u minus 10 over z minus 0.8 multiplied by the u. So now we can take the u with the first root as the first state variable, and we can take the u with the second root as a second state variable. So here now we can write y is equal 10 x1 minus 10 x2. So y of k will equal 10 x1 of k minus 10 x2 of k, where x1 is equal to u over z minus 0.9. So simply from here we can find x1 of k plus 1 minus 0.9 x1 of k is equal u of k. If I rearrange it, x1 of k plus 1 will equal 0.9 x1 of k plus u of k. The last one, x2, which will equal u over z minus 0.8. This one we can write as rearranging x2 of k plus 1 will equal 0.8 x2 of k plus u of k. So simply now we finish writing the state space representation using the direct or the parallel, using the parallel programming. Now in the direct programming or the phase canonical form, if we recall, I can write it as x of k plus 1. I will write it directly in matrix form, second order, so 0 1 x of k plus 0 1 u of k. Now here I will start with the coefficient of the z minus 1 inverted in the sign, so minus 0.72, and here it will be 1.7. Now because here we have only 1, so this means that y of k is equal x1 of k. Now this is the direct programming. Now for the parallel programming, if we recall, we have the x of k plus 1 equal to 0.9 0 0 0.8 x of k plus, here we have input in the first equation and the second equation, u of k. Now y of k was equal to 10 minus 10 x of k. Now this is very interesting because those are two different representations, state space representation for the same transfer function or the same system, which we can conclude that the state space representation is ununique. So for the same system we can have different representation. Now for the direct programming, we notice that the last line here contain very fruitful information regarding the characteristic equation. So from here, if I need to write the characteristic equation, the order here is 2, so I will start from z to the power 2. Then this will be the coefficient of z, inverting the sign, and this will be the coefficient of z to the power 0. So this is the characteristic equation. If I compare it, yes, this is the characteristic equation. Now for the parallel representation also we have very fruitful representation such that we having the roots of the characteristic equation. The roots. So if I need to write the characteristic equation, simply here I'm having two roots, so z minus 0.9 multiplied by z minus 0.8 is my characteristic equation. And simply why we are discussing the direct programming and the parallel programming, because they are useful representation. We have a direct link between the transfer function and the state space model. We can have access in the direct programming to the characteristic equation directly. In the parallel programming, we have a direct to the characteristic equation, but also we have a direct to the solution of the characteristic equation. We have the roots of the characteristic equation. Let's assume that given the following simulation diagram, and we need to write the state variable. So it will start with this multi-variable system, so u1 of k. Let me plot it here. Here we have a shifting register or unit delay, so t. Here we have the y1 of k. Now here we have a constant which is the 0.5, and here we have the second input u2 of k, and we have direct. The second input is also injected to the first input or the first system. Another unit delay here, and let's assume this is y2 of k. Here we have a connection with gain equal to 2, and here we have a negative unity feedback, some minus. Now let's assume I'm having a direct input here. In order to highlight the D, and we need to find the state space representation. So given that this is the x1 of k, and this is the x2 of k. So if this is x1 of k, this unit delay, then this will be the x1 of k plus 1. The same thing, this will be the x2 of k plus 1. So let's try to write the first equation. x1 of k plus 1 will equal. The first thing here we can write is the 0.5 x1 of k. Then here we have u1 plus u1 of k, and here also we have the u2 plus u2 of k. Now the same thing we can do it for the x2 of k plus 1, which will equal minus x2 of k plus u2 of k. Now if we increase the complexity of the system by adding, let's assume, another connection here, this will be plus x1 of k. So in matrix form, x of k plus 1 will equal to here I'm having two input, u1, u2, and here I'm having the x of k. So the first one here is 0.5. I'm reading the first equation. I don't have x2, so 0. I'm having 1 and 1 as the gains for the input, the first and the second input. The second line here I'm having for x1 I'm having 1, for x2 I'm having minus 1, I'm having only the u2, so this would be the 0 and the 1. So now what about the output? Let's try to write the output. y1 here is equal to what? Now y1 of k will equal x1 of k plus 2 x2 of k. Now what about y2 of k here? y2 of k will equal x2 of k, and I'm having direct input, so plus u2 of k. So in matrix form, this means that y of k will equal to now y1 of k was equal 1 for the x1 and 2 for the x2. y2 I'm having only x2, so this would be 0 and the 1. For the input here I'm having no input, so 0 and 0. Here I'm having the u2, so 0 and 1. So this is the state space representation from a simulation diagram. So here again, if you notice here, the output of the unit delay is a state variable. So simply here I'm having two shift register or unit delay, so I need two state variable. So now let's discuss the relation between state space and transfer function. the A, the B, the C, the D, the matrices of the state space representation, and the transfer function. So simply we state that x of k plus 1, the general representation for a state space model, is A x of k plus b u of k. Now if we are taking the z transform for this equation, according to the property of the z transform, I can distribute it. So z of x of k plus 1 will equal the z transform for a x of k plus the z transform for the b u of k. So here this will equal z x of z minus z x of 0, which will equal to a x of z plus b u of z. So now this can be written as z multiplied by the identity matrix minus a x of z will equal to z x of 0 plus b u of z. Now where I is the identity matrix. So x of z will equal to zi minus a inverse multiplied by z x of 0 and multiplied by this term, so this will be zi minus a inverse multiplied by the b u of z. Now if you assume that x of 0 is equal to 0, then let x of 0 is equal to 0, then we have x of z is equal to zi minus a inverse multiplied by b u of z. Now remember, the state variable contain also the output equation. So if we take the z transform for the output equation, which is the y of k, which will equal to the z transform of the cx of k plus d u of k, then y of z can be written as cx of z plus d u of z. Now if we substitute the x here, we'll get y will equal to c zi minus a inverse b u plus d u. So simply this means that the transfer function, which is the y over the u, is equal c zi minus a inverse b plus d. And simply if d go to 0, if there's no d, if there is no direct input in the system, Then the transfer function now, y over u is equal c zi minus a inverse b. Now let's discuss the solution of the state equation. So we need to find x of k, and this will equal to a to the power k x of 0 plus the summation from j equal to 0 up to k minus 1 a to the power k minus 1 minus j b u of j, and y of k will equal this x multiplied by the c, so it will be c a of k x of 0 plus the summation from j equal to 0 up to k minus 1 c a k minus 1 minus j b multiplied by u of j. And if we have a direct input, it will be here plus d u of k. Now, if we are discussing the unforced system, for the unforced system, the meaning that u of k is equal to 0, and only we are discussing the response due to the initial condition. So in this case, if we use the recursive method, x of k plus 1 will equal a x of k, and using the recursive method we can say that x of 1 will equal a x of 0, x of 2 will equal a x of 1, which actually a square x of 0, and we can continue, for example, to x of 3, which will equal a x of 2, which will be a to the power 3 x of 0. So simply using the recursive method, we can reach that x of k is equal a to the power k x of 0. So simply the a to the power k is called the state transition matrix. So now here we can write that phi of k, which is the state transition matrix, is equal a to the power k. So phi of minus k is equal to a to the minus k, which actually ak inverse. And if we have phi of k1 plus k2, this can be written as A of k1, A of k2, so this will equal to phi of k1 multiplied by phi of k2, and phi of 0 is equal to the identity. And if A is diagonal, then assume A is equal to A 0 0 and B, then A to the power k will equal to A to the power k here 0 0 B to the power k. Now we need a method in order to find the state transition matrix. Now if we take the Z transform for the unforced system, X of Z will equal to Zi minus A inverse Z X of 0, and simply if we recall the solution of the recursive system, X of k which equal A of k X of 0, we can say that the state transition matrix phi of k which equal A to the power k will equal the inverse Z transform of the Zi minus A inverse Z. So let's discuss the following example to highlight how to find the state transition matrix. So here let's start with the example. So consider the following transfer function. Now here we need to represent it in the state space model. So if I'm using the direct programming, X of k plus 1 will equal a 2 by 2 matrix, 0 and 1 here. Here I'm having the X plus 0 and 1 for the U. Now here I need the coefficient of the Z to the power 0 inverting the sign, so minus 2. Here I will put the coefficient of Z to the power 1 minus the sign, so minus 3. And Y of k, I will go to the denominator, and here will be the coefficient of the Z to the power 0, so this will be 3, and here to the coefficient of Z to the power 1. Now if I need to use the parallel, I will factorize it. So G of Z will equal Z plus 3 over Z plus 1, Z plus 2. So this can be factorized to certain gain k1 over Z plus 1 plus another gain, let's say k2 over Z plus 2. You can calculate the gains. So Now if I need to write it, so x of k plus 1 will equal 2. Here I'm having the first root, which is the minus 1, 0, 0, the second root, which is the minus 2, multiplied by x of k plus the inputs. Here I'm having 1 and 1, and this is the u of k. For the output y of k, here I will have k1, k2 multiplied by x of k. So if I'm using, let's assume, the direct programming, so this will be the A matrix. So now if I need to find phi of k, I need to do the z inverse of the zi minus a inverse. So now let's calculate this one. Z I minus a, this will equal to z here, minus 1 here, 2 here, z plus 3 here. Now the inverse for this one will equal 1 over the determinant. Then I'm switching the diagonal, so this will be z plus 3, and this will be here the z. Then I'm inverting the sign of the diagonal, so this will be the 1 minus 2. Now you know how to calculate the determinant. The determinant is equal z plus 3 minus of minus, so plus 2, which actually the same as the characteristic equation, which is z squared plus 3z plus 2. Zi minus a inverse, which will equal to, the first one is z plus 3 over the determinant. The second one is z over the determinant. The third one is minus 2z over the determinant. And lastly we have here z, so this will be the z square over the determinant. So phi of k will equal to the inverse of the first one the z inverse for the second one, the z inverse for the minus 2z over delta, and finally the z inverse for the z square over delta. Now you can use either the partial fraction expansion to locate the inverse z transform, or the residual method in order to calculate the inverse z transform. If we do the math, this will equal 2 minus 1 to the power k minus 2 to the power k minus 1 to the power k minus 2 to the power k minus 2 minus 1 to the power k plus 2 minus 2 to the power k, and finally here we have minus 1 to the power k plus 2 minus 2 to the power k. And this is the end of chapter 2. So see you when discussing chapter 3. And this is the end of chapter 2. So see you when discussing chapter 3.